All right, welcome back, everyone. Today's explainer is going to take a hard, tangible look at the actual physical infrastructure of the web. We're going to literally trace the exact anatomy of a digital message from the very millisecond you hit send all the way to the moment it arrives at its destination.
Think about it for a second. Every single time you click a link, or stream a movie, or just send a quick text, you are personally triggering a massive global chain reaction. It all happens in milliseconds, but the underlying process is just beautifully complex. So, before we start tracking our packets of data, we need to establish our foundational definition. What exactly is the Internet?
Okay, let's dive right into this. We can actually define the Internet in two very distinct ways. The first is what we call the nuts and bolts view. In this perspective, the Internet is literally just a global system of interconnected physical devices. You know, things like smartphones, laptops, servers. And they are all wired together through communication links and routers. It's basically a massive physical machine. But then we have the second view, the service view. This looks at the Internet as a vast infrastructure that provides services to distributed applications. It's the underlying platform that allows the whole shebang, your email, web browsing, video streaming, online gaming, to even exist and function. Both of these views are absolutely true. But to really understand how a message moves, we're going to focus heavily on those nuts and bolts.
To navigate this massive machine, here is our roadmap for today. 1. What is the Internet? 2. Speaking the same language. 3. The physical pathways. 4. Navigating the network core. And finally, 5. Traffic jams and delays. Let's get to it.
Starting off with Section 1. What is the Internet? Looking specifically at the edge of the network.
So, the crucial takeaway here is that you and your devices live at the absolute edge of the network. See how the mobile networks, the home networks, and the enterprise networks are all kind of clustered on the outside? That right there is the edge. This is where our end systems, which are also known as hosts, actually live. When you open up a web browser on your smartphone or you fire off an email from your laptop, your device is acting as a client host on the edge, and it's requesting a service from an always-on server, which happens to also be located somewhere out there on the edge. Basically, the edge is the starting line for absolutely any data we request or send.
Moving on to Section 2, speaking the same language, or the rules of engagement.
This brings us to a really fundamental concept, and that is the protocol. In the networking world, a protocol strictly defines the format, the order of messages exchanged between two or more communicating entities, and the specific actions that need to be taken when a message is either transmitted or received. You could basically think of a protocol as the absolute unbreakable etiquette and law of the digital world. Because honestly, without protocols, all those millions of wires and routers wouldn't mean a single thing. The machines literally just wouldn't understand each other.
And I love this comparison because it brilliantly illustrates exactly what we mean. Over on the left, we've got a standard human protocol. One person says hi, the other person replies hi, then one asks, got the time, and the other replies 2 o'clock. It's a very structured, predictable exchange, right? Well, on the right, we see machines doing the exact same thing, but using network protocols. A computer sends a TCP connection request to a server, the server fires back a TCP connection reply, and only then does the computer request a specific file. It's rigid, for sure, but that predictability is exactly what ensures that billions of devices made by thousands of totally different companies can all communicate flawlessly.
All right, Section 3, the physical pathways. Let's look at guided and unguided media. We call the physical roads of the Internet links, and they generally fall into two main categories. The first is guided media, which simply means the signal is physically guided through a solid material. This totally shatters the illusion of some invisible, magical internet cloud. Your data is literally traveling over physical, insulated copper wires called twisted pairs. Or it's zipping through coaxial cables, which use these concentric, heavily shielded copper conductors that are super common for shared cable TV and internet. But the real star of the show today is fiber optics. These are incredibly thin, flexible strands of glass that conduct actual pulses of light, where a single pulse represents a bit of data. They support tremendous gigabyte speeds. I mean, your bits are literally flashing as light across the bottom of the ocean. How wild is that?
But hey, you aren't always plugged into a wall, right? When we don't use wires, we rely on unguided media. This means our data bits are just propagating freely as radio channels in the electromagnetic spectrum. And these are organized really neatly by the distance they need to travel. For just a meter or two, we use short-distance radio. Think your wireless headsets or keyboards. Need to cover your whole house or office? We use local area radio spanning a few hundred meters, which is your everyday Wi-Fi.
But for wide area coverage across tens or even thousands of kilometers, your message might actually be beamed straight up into space. It links to geostationary or low-Earth orbiting satellites, which regenerate that signal and beam it right back down to a ground station.
Which brings us to Section 4, navigating the network core and how data actually transfers.
Now, what's really interesting about this visual is the sheer density of what is happening right in the middle. Look at all those interconnected routers forming that chaotic mesh in the network core. The fundamental question network engineers had to solve was, how exactly do we transfer data efficiently through this crazy web? When your message finally arrives here from the edge, how does a core actually decide where to move it next?
Well, historically, early networks used something called circuit switching. This is exactly how old-school telephone networks worked. If you made a call, the network literally reserved a dedicated physical circuit strictly for you for the entire duration of that call. It guaranteed your space, sure, but it was incredibly wasteful. If you paused to take a breath, that reserved bandwidth just sat there, empty and unused. It was super expensive and completely unscalable for something as massive as the internet. So the modern internet relies on a massive conceptual leap called packet switching. Instead of reserving a whole dedicated road for just one car, we take your data stream and chop it up into discrete little chunks called packets. Every user's packets share the exact same network resources, just squeezing in wherever there's room and using the bandwidth only as it's actually needed. It's highly scalable and super efficient, but because it's a shared environment, it introduces a very modern headache: congestion.
And that shared highway leads us straight into Section 5, traffic jams and delays, dealing with resource contention.
Because the internet relies on this packet switching, routers have to handle data using a process called store and forward transmission. Let's just walk through this step by step. First, as we know, the source breaks the message into smaller packets. Second, a packet races down a wire and arrives at a router in the core. Now, here is the absolutely crucial part, step 3. The router, or node, cannot just pass the data along on the fly. Actually, scratch that. It literally must receive the entire complete packet and temporarily store it before it can push even the first bit out the other side. Only after it has the whole chunk does it move to step 4, forwarding the packet onto the outbound link. Moving one hop at a time like this is absolutely vital for data integrity, but it takes time.
And when you add up the time it takes to do this store and forward process across dozens of routers, you get what we call nodal delay. You guys, this right here is the literal anatomy of why your streaming video sometimes buffers. It all starts with resource contention. When the aggregate demand from everyone in your neighborhood watching Netflix or sending emails suddenly exceeds the available bandwidth of a router. Because of that traffic jam, packets literally have to wait in line, creating a queuing delay. Then you've got transmission delay, which is the actual time it takes the router's hardware to push the bits onto the wire. Thankfully, as our tech gets better, that delay decreases. But finally, there's propagation delay, which is just the unyielding physics of the universe. The actual time it takes for a bit to physically travel the length of a copper wire or a fiber optic cable across an entire continent. All these little delays accumulate, hop by hop, router by router.
And yet, despite the chaotic sharing of resources, despite the physical limits of light and copper, and the constant, everyday threat of queuing delays, it just works. Billions of devices, successfully communicating trillions of packets every single second. It really makes you wonder, doesn't it? How does this massive, delicate web of shared wires and incredibly strict rules manage to keep our entire modern world running without just collapsing under its own weight? It's a sheer mechanical marvel of human engineering. The next time you click a link and a page loads instantly, take just a second to appreciate the invisible, physical infrastructure that flawlessly delivered your message across the globe. Thanks for joining me on this explainer. Keep wondering, keep learning, and I'll catch you in the next